This video series is about inferential methods when you have multiple samples and a quantitative response variable. In the videos so far in this series, I have looked at 3 different two-sample randomization tests. In this video, I want to summarize what we have learned from these videos and give a general framework for two-sample randomization tests. If you've watched the videos up to this point in this series, it probably has the feel of doing the same procedure over and over. It feels that way because that is exactly what we are doing. The only difference is what score transformation we use. This can lead us to set up a general framework for two-sample randomization tests. The required R packages you will need in order to follow along with this video is just nplearn. Here's the setup. We use this setup in each of the previous 3 videos. We have 2 existing populations to be compared. That is, we may take 2 samples from 2 different populations, but more commonly, we sample from one existing population, randomize to conditions, and then create a potential population by applying a treatment in one of our conditions. We have independent observations within each sample and a quantitative response measure. The test statistic that we have been using is the sum of scores in the smallest sample. In general, we use T as the sum of R, where R is the replacement score. If you are going to do a Fisher-Pittman type randomization test with original scores, then R becomes the original score. If you're going to do a Wilcoxon rank sum test, then R, the replacement, is the rank of the original score. If you're going to do a normal scores test, then R, the replacement score, is a van der Waerden normal score. And if you want to do the Fisher-Irwin test, then the replacement score is either a 0 or 1. I did not do this last one in previous videos, so let's look at it now. The result may surprise you. In another video series, I introduced a test for the difference of medians that reduces to the Fisher-Irwin test. We looked at the employee satisfaction in companies with and without feedback systems. Here again are the data. Higher scores represent higher satisfaction from the employees in that company. 12 companies are represented here, and 7 of those companies do have employees' feedback systems. The other companies, the other 5, do not. I need to use a common median and determine how many scores are above and below the median in each condition. So here I'm calculating the common median using the combination of scores from each of these 2 conditions. Then I'm calculating how many scores are above the median in the EFS condition and how many scores are above the median in the no EFS, that is, no employee feedback companies. Now, the fact that we're doing a median test, as I pointed out when I introduced the Fisher-Irwin test, means that we know in advance how many scores are going to be above and below the median. That is, because we have 12 scores, 6 have to be above, 6 have to be below. What we don't know is which kind of companies these will come from. But here are the results. We see that for the companies with feedback systems, we have 6 scores that are above the median, 1 is below, and with no employee feedback system, all 5 of the companies are below the median. That outcome we did not know before we actually looked at the results, even though we did know, based upon using a sample of size 12, that 6 would be above the median and 6 would be below. The fact that we did know means that we have to use the hypergeometric distribution rather than the product binomial, but I'm going to do it a little bit differently than both of those right now. I am going to use the same randomization test procedures that I used in the first 3 videos in this series. we will use 0 and 1 for below and above the median. Notice that I'm doing the same thing I did in all the other videos in this series. I'm creating a list of the combined scores. Those scores are just zeros and ones here. And then I'm going to create a distribution based upon my exact two-sample distribution procedure, taking those combined scores of zeros and ones, and then creating a distribution based upon the smallest sample size, that is 5. I'm only going to look at the first 25 values in the distribution rather than showing the whole thing in order to keep this more manageable. You'll notice that there are many different combinations that can lead to a score of 0. So if I wanted to look at the probability of all of these together, I would have to look at the cumulative probability here up to the last 0 in the list, and that cumulative probability is 0.00757. Similarly, if I wanted to look at the ones, I would have to go all the way up and obtain the value of 1 that has the highest cumulative probability associated with it. But in this particular case, notice what our value of the test statistic is. It is the sum of the above median, that is, how many ones do we have in the no EFS group. Why the no EFS? Because I'm focusing on the group with the smallest sample size. And it turns out, as we already noted, that there are 0 values that are above the median. So if I go back to this table, all I need to look at is the cumulative probability here for 0, and that is 0.0076 or about 0.008. And I look here, and here, sure enough, that is what I list as the p-value. Now, originally, we learned how to use this test in the video series on multiple samples with a categorical response, and we did the Fisher-Irwin exact test, what many people call the Fisher exact test. We have 6 out of 7 successes for the EFS condition, that is above the median, 0 out of 5 in the no EFS condition. And so what we're doing here is listing these outcomes in a matrix because that's what's required in the R function for the Fisher exact or the Fisher-Irwin test. The alternative hypothesis is less because the way I've listed them is to match up the way that I just did it, where we're focusing on the no EFS group. And notice what we get here, a p-value of 0.007576. So as you can see, we used our general form of the randomization test to get the same result as obtained with the hypergeometric distribution. So we really have 4 kinds of replacement scores: original scores, ranks, normal scores, or zeros and ones. The two-sample randomization test is a general method for testing for median equality when there are 2 independent samples with independent observations. Here's a list of the primary considerations when selecting a transformation. First, you should consider the nature of measurement of the response variable. If it is a categorical measure, such as a dichotomous measure, we went over methods back in the multiple samples with a categorical response variable series, and you should take a look at that. But we revisited one of those in this multiple samples with quantitative responses. Even though 0 and 1 really isn't a quantity, it still can be done using a randomization test. If we have ordinal measurement, we'll want to stick with ranks, and recall from a previous video, we'll also need to change the hypothesis, and instead of looking at the equality of medians in the 2 distributions, we instead are going to look at probabilities of obtaining a certain size score from one distribution as compared to the other. If we have quantitative data, then the world's our oyster. We have a wide number of choices. We should consider the condition of shape equality. If I cannot assume shape equality, Not all is lost. I can look at the probability of obtaining a lower or higher score depending upon the direction of our hypothesis from one group as compared to the other to see if they're equal or if it's more likely that lower or higher scores come from one condition. You could consider, for instance, if we have a control and a treatment, and the treatment is supposed to raise scores, that we would expect the higher scores to come from the treatment condition. So unlike when we did two-sample parametric inference, in which we were using the t-test, we now have an option when we don't have shape equality. When we're using the t-test, not only do we assume that we have shape equality, we assume that the shape is a normal distribution. Here we do not have to worry about that. Then the final thing to consider is the nature of the population distribution. Is it light-tailed? That is it platykurtic? Does it have a lower peak and lighter tails? Is it a normal or close to normal distribution? Or does it have heavier tails than a normal distribution? In many behavioral and social measures, research has found that most of the measures that we use have distributions that have heavier tails than normal. In that case, I may want to consider using ranks as replacement scores. I might also want to consider using ranks as replacement scores if I don't know anything about the nature of the distribution, simply because I know that my power will not drop off too bad if that distribution is really not favorable to ranks, but could get substantially higher if it is, such as when I have heavy-tailed distributions. So we have a general method, we have a general framework, and we have considerations to help us choose among the various tests that we can apply with that general framework.